All right, welcome everybody. Thanks for coming to Life of a Packet and Death of a Legacy. My name's Cynthia Thomas. I'm a systems engineer at Metonet. So some of the things we'll talk about today, death of a legacy, talking about specifically legacy network infrastructures and solutions that are out there, and get into the evolution of network virtualization overlays, specifically for cloud architectures, Neutron plugin specifically to OpenStack, and we'll talk about a solution called Metonet. We'll go through life of a packet, specifically of the OpenStack Cloud, using Metonet as a Neutron plugin. Finally, we'll talk about packet behavior, and what I mean by that is how you can manipulate and treat traffic, as well as monitoring tools that you can use with this new technology we'll talk about, network virtualization overlays. All right, so let's talk about the tale of a legacy and its successors. So the evolution towards network virtualization. So for those who might be familiar, like myself, coming from a hardware networking background, be quite familiar with this type of infrastructure, the three-tier architecture, built with complex hardware networking products, meant, in a pre-virtualization era, where north-south traffic flows were more prevalent. So aggregating traffic, pushing it around, typically proprietary white boxes, for example, or proprietary hardware networking, for example. So building infrastructure within a data center, of course, you need to protect the network. So installing a firewall, typically a hardware device in the network, implementing NAT for north-south traffic bound flows for external access. Then, of course, in good measure, deploying those in pairs for high availability. As other types of workloads were coming into this infrastructure, we need load balancing, for example, web scale type applications, deploying those in pairs. But what's obvious here is, these are specific devices and appliances within the network. So these typically form traffic trombones, bottlenecks in the network, pushing towards particular service appliances within the network for specific higher layer network services. And going back a little bit here, as virtualization workloads became more and more prevalent, using that existing infrastructure forced different proprietary protocols to be formed, expanding layer 2 networks, large broadcast domains using proprietary technology or other technologies like spanning tree protocol to allow to build those large layer 2 domains. And anyone who's used spanning tree knows it's a scary thing. Instability of the network, chatty broadcast domains, reconvergence, all those things that we don't want to deal with. And that being said, even the author of spanning tree admits, the use case was for much smaller networks, not meant to scale the way we'd like to. So using that existing infrastructure that we did have, with more and more virtualized workloads, the move to cloud, using that for OpenStack. Let's put OpenStack on top of all that. And those who are familiar from OpenStack's networking early days, these came through several projects. So initially it started as Nova networking, flat VLANs, but that was really just the same problem we had with the large layer 2 domains, configuring the network with VLANs, dealing with these large layer 2 domains. Then Quantum and Neutron came about, so Nova networking dealing with the VLANs, Quantum and Neutron architected early on. They did have single points of failure in their architecture, specifically the Neutron network node to achieve higher layer services like layer 3 routing, IP tables for security groups, et cetera. And as Neutron develops and grows and continues to grow with different solutions, there still is that, there still hasn't been that escape in some solutions for certain bottlenecks in the network. Let's say controllers for doing higher layer services, or SNAT still residing on the Neutron network node. So the evolution is still continuing for various plugins. But bottom line is not all of them have totally escaped the bottleneck scenarios for certain higher layer services. So disadvantages with legacy network architectures, a bit of a blanket statement for both pre-virtualization era as well as OpenStack. But they were architected at a time when a majority were physical workloads. So kind of adapted the infrastructure we had to be used in environments where OpenStack was going to be laid out. So already the proprietary hardware was laid down, proprietary technologies, sort of more of a closed type environment. Bottlenecks for those higher layer services, so pushing traffic towards service appliances in the network, as we depicted earlier. So bottlenecks towards those things. And for preliminary type neutron plugins, single points of failure. And it was pretty evident in proof of concepts for OpenStack that certain architectures for neutron plugins introduced these single points of failure. So inevitably, that was not good for scaling the way we want to scale with OpenStack. So scary things here. So that being said, let's talk about network virtualization overlays as a solution for cloud networking. So the nascency of the MVOs. We talked about all these higher layer services previously, solved by particular vendors, service appliances, separate networks forming bottlenecks in the network, traffic trombones towards those devices. Moving towards network virtualization overlays, we get that agility that we want with cloud networking. So giving the ability for tenants in OpenStack, for example, to build and tear logical networks. So logical topologies built to scale, not introducing single points of failure in the network, and doing this in an efficient manner for higher layer services through a single virtual hop. So just considering it as more efficient networking. So some of the advantages of network virtualization overlays with a completely distributed architecture are pushing that intelligence right to the edge. So, perhaps through an agent at the compute host, handling all the higher layer services, having that intelligence at the edge in whatever needs to be applied for packets being sent out that compute host. Eliminate the single point of failures, making your cloud networking highly available, and architect that to scale out. So in a scenario where you don't have these single points of failure or particular service appliances, like a layer 2 service node or a controller, then you push the power of the cloud to the edge. So the routing decisions or higher layer services are done right at the edge. So this enables the rapid creation of logical networks at the whim of a tenant. So I'll talk about Metonet as a completely distributed architecture with no single points of failure, where a lot of the intelligence or all of the intelligence is at the edge on an as-needed basis. So Metonet is a software network virtualization overlay done completely in software, achieving layer 2 through 4 services in a completely distributed manner, and is meant to run over any existing infrastructure. So you can use your legacy infrastructure if you want. Recommendation more is to use more simpler to deploy layer 3 routing protocols, build a solid layer 3 class, not to worry about layer 2 large broadcast domains, nor pushing towards any particular service appliances to remove bottlenecks in the network. Oop, sorry, I hit escape. Just from right there? Sorry. All right, so life of a packet, specifically OpenStack with Metonet networking. So as an administrator of an OpenStack cloud, Metonet automatically creates a provider router when an administrator goes in and creates an external network, so for external access for tenants. So that's created automatically in the backend. So tenants, leveraging OpenStack as a self-service portal to build their logical topologies and workloads, they can go into Horizon or Neutron CLI, build their tenant router, build their tenant network, apply a floating IP address, apply whatever rules they want through security groups, allow or deny rules for certain ports or IPs, and define those security group policies. So So let's see what happens when we want to send traffic across this network. Let's spin up 2 VMs on the network. So once the tenant has gone in and created these logical topologies, Metonet is storing all this logical information, topology information, in the network state database. So what happens when that first VM starts sending a traffic, on the very first outbound packet, and this being only the very first, otherwise it would be cached or already programmed locally. The first outbound packet, the Metonet agent intercepts the call in user space and queries the network state database to find out that virtual topology specific to that tenant in whatever manner they may have built it. So of course it's logical, so that logical topology is being pulled down to the compute host, to the agent. Then that local agent on the compute host, the ingress compute host to that path, is actually doing a simulation of the packet flowing through this logical topology, whichever direction is meant for, whether it be external network, whether it be for another tenant's VM, and applying whatever rules, security group policies that may be the fate of that packet. So whether that be NATs, load balancing, that'd all be done in simulation, figured out, manipulated on the packet, and can be sent over the VXLAN tunnel, which was set up and received by the destination compute host. Once that simulation is done, all the remaining packets for that traffic flow can be sent at near line rate, just the overhead of the VXLAN tunnel. So let's talk a little bit about packet behavior, some of the cool things you can do with Metonet, empowering you to manipulate traffic a little more on the network in an OpenStack Cloud, for example. So some things you can do are policy-based routing. You have this ability to add routes based on source or destination. Subnets point them towards a virtual device. So that has a lot of great implications for control of the type of traffic that you can send through a network. Other things, the equivalent of ACLs, they translate specifically to our lower level rules and chains. So you can read a little bit more about that on our Metonet blog. So here's an example of rules and chains already automatically created in the case where a tenant has spun up a VM, applied a FIP. We automatically create the rules. For example, some of the NAT functionality is seen here in this output. So those types of things get translated. But you, as a user or tenant administrator, have the ability to go in, control those things, manipulate anything on the layer 2 through 4 packet tuple, position it within these rules and chains, drop, allow, deny, as you wish. So a lot of control for the administrator. Once you've gone crazy and changed all those things, how are you going to monitor it and troubleshoot these things? Legacy tools we used in the past, like RSpan, for example, port mirroring, NetFlow. Looking at the type of packet that's coming off of these compute hosts, they're going to look a little different. How are you going to make sense of that? Because now we're specific to logical topologies now. So some of the other cool things in Metonet Manager allows you to have the ability to troubleshoot a little better. So we have flow tracing tools. This allows you to input traffic conditions specific to those parameters and capture packets, and will basically display the type of virtual policies that you've gone through, the virtual topology, the types of rules and chains that were applied, and in the end, the fate of the packet. Whether it's to send a packet or drop it based on a rule, for example. If you weren't aware, Metonet is open source, so you can try it out for yourself. You can go to metonet.org. We'd love to have you join the community as well. Be a user, be a contributor. We'd love to have you be a part of our community, so you can check that out. Our biggest method of communication is Slack, so get signed up, and we'll hope to see you on Slack. So thanks for your attention today.